Hello, my name is Tyler Estro. I'm going to talk about our work desperately seeking optimal multi-tier cache configurations. This is a joint work between Stony Brook University and Emory University. I'll first provide a general introduction to our work, including its motivation and key contributions. Followed by that, I'll discuss our proposed best practices for cache analysis. I'll then describe the important features of a multi-tier simulator and the design of our experimental simulator. In the evaluation section, I'll present some interesting and counterintuitive results, and finally I'll conclude with some closing thoughts and the future of our work. The vast configuration space of multi-tier caching enables the design of very complex systems. Any number of virtual or physical devices can be arranged as tiers of cache or persistent storage. These can be implemented within different infrastructures such as VMs, cloud storage, or distributed systems. New types of devices are constantly emerging as well, introducing additional complexity and configuration options. Workloads and access patterns are also evolving. The volume of data we access continues to grow, and we're seeing more complex access patterns and increased multi-tenancy. These all greatly impact the frequency and distribution of data reusage, two of the most influential factors in any caching system. It's vital that our methods of evaluating cache mature along with storage technologies. However, cache analysis practices are short-sighted. They often focus solely on performance. Miss ratio curves are a prime example of this. These curves plot the ratio of cache misses as a function of cache size for a given workload and eviction algorithm. And they do have many uses, like evaluating eviction algorithms' performance or guiding allocation, but they don't extend well into multi-tier systems. We also frequently see evaluations that don't use a comprehensive set of metrics. So for example, examining performance metrics such as latency may be misleading without also considering the cost of purchasing and using the cache. Physically experimenting with many cache configurations is far too costly and time-consuming. The most feasible solution would be an accurate and efficient N-level I/O simulator. There are some advanced CPU cache simulators available, but storage cache simulators are scarce and lacking. State-of-the-art simulators are mostly outdated. They could either simulate only a single tier or some fixed set of tiers. They're missing key features, offer limited analysis tools, or aren't easily extendable. So as a result, it's commonplace for researchers to develop their own proprietary simulators to evaluate specific applications, and then never release them to the public. In this work, we propose best practices in cache research, including the analysis of multi-tier configurations and a more comprehensive set of evaluation metrics. In this section, I'll discuss cache analysis techniques and relevant metrics. There's a dollar cost per byte increase when purchasing hardware with better performance, so it follows that cache performance is constrained by cost. If this weren't the case, everyone would store their data in massive amounts of the fastest DRAM available and just back it up with a giant battery. Due to their strong relationship, best practice should be to evaluate monetary cost and performance together whenever possible. Storage research has been trending towards the analysis of more application-specific metrics as opposed to raw performance. Tail latency is an important quality of service metric for cloud and web services, as well as at the hardware level. Total cost of ownership is a comprehensive metric that considers everything that contributes to capital and operational expenditures, and intercache and network traffic can be used to detect congestion between tiers of cache that cause bottlenecks in a system. Simple performance metrics can be useful, but cache analysis should be conducted using a more diverse set of metrics whenever possible. We also need to create complex metrics that reveal critical design trade-offs, such as throughput per dollar. The argument can be made that improvements in cache performance translate into a reduction in cost. However, complex interactions between tiers produce scenarios where the relative performance per dollar between configurations is very different. Cache operations such as evictions and flushing dirty data have effects that cascade throughout the entire storage system. So a cache eviction policy that improves miss ratio in your DRAM or SSD may actually result in worse performance if it requires the hard disk to do even a little bit more work. Even with improved performance, the SSD may wear out quickly, and purchasing a replacement drive could make it a less cost-efficient configuration over its lifetime. So best practice should be to analyze multi-tier configurations whenever possible. Visualization is a powerful tool that enables users to explore large and complex data, facilitating better understanding and decision-making. Trends and objectives such as performance or cost can't easily be visualized in multi-tier systems where cache size is no longer one-dimensional. We're working on visualization techniques that employ multi-dimensional Pareto frontiers to locate optimal cache configurations. In our past work, we developed an interactive visual analytics tool to explore a massive data set of storage benchmarks containing many numerical and categorical parameters. Multi-tier caching is an excellent candidate for this type of analysis, and we're currently collaborating with visualization experts on an interactive tool as well. Next, I'll enumerate the important features of a multi-tier cache simulator, introduce a trace upscaling technique, and describe the simulator we developed. A properly designed multi-tier I/O simulator should contain a rich set of features and be general enough to model any cache hierarchy. Write policy is typically chosen based on data consistency and recoverability needs, but it can have a massive impact on performance in multi-tier systems. Emission policies that utilize historical metadata and machine learning can more effectively moderate data emission. Similar to write policy, the impact of inclusion policy is amplified in multi-tier systems, since enforcing it can result in I/O cascading throughout the system. Researchers have developed global aware eviction algorithms where a single caching policy manages data replacement in all caches. A simulator needs to efficiently simulate numerous configurations for any given workload, but traces can be massive. Miniature simulations uses a spatial hash-based trace sampling technique that drastically reduces the size of a trace while accurately retaining cache behavior in a similarly scaled down cache. This allows us to evaluate large caches that access substantial data and is essential to a modern simulator. Prefetching algorithms like Mithril introduce a prefetching layer which exploits historical patterns and cache request associations. A simulator should be flexible enough to allow prefetching that can interact with any tier in the system. Multi-tier caching only makes sense when you have a large amount of data. If your entire data set fits into the DRAM of an average laptop, then there's really no benefit to adding an additional caching device. The problem is that simulating large traces is extremely time-consuming. So as I mentioned in the previous slide, miniature simulations alleviates this problem. But what if we have the opposite problem, where our trace only accesses a small amount of data? Our solution is to apply miniature simulations in reverse, by treating the trace as if it's a scaled-down version of a much larger trace. We confirm the soundness of this technique using synthetic traces, as well as with Dr. Waldsberger. Accuracy on real-world traces will vary, but it's still a useful tool for what-if analysis and modeling multi-tier systems. To demonstrate the utility of our proposed simulator, we extended PyMimircache. PyMimircache is a single-layer cache simulator developed as a Python framework with an efficiency backend. It supports numerous eviction algorithms and provides several analysis tools, such as miss ratio curves or reuse distance distributions. PyMimircache was designed to simulate a single cache, so it has no concept of backend storage and doesn't differentiate between reads or writes. We added this functionality and implemented both write-through and write-back policies. We utilize a MySQL relational database for experimental results and Elasticsearch for metrics we calculate using those results. MySQL provides us with a neat and reliable way to store experiments along with their configuration parameters, while Elasticsearch allows us to quickly access metrics for visualization and analysis. We simulate multi-tier systems by running serial instances of PyMimircache, which I'll describe in the next slide. So we start with the original trace of some workload. A high-level script containing the current experiment's configuration parameters, including cache size, write policy, and eviction policies, passes the parameters and original trace to the first instance of PyMimircache. This instance acts as our first cache, L1. The L1 instance produced two forms of output. The first output is an operation log that gets written to our MySQL database. Our extension keeps track of all cache hits and misses, as well as counts of all the resulting read and write operations. The other output is a new intermediate trace, which contains requests from the original trace that resulted in a cache miss in our L1 simulation. Once the L1 instance is completely finished executing, the intermediate trace is fed as input to a separate instance of PyMimircache. This new instance acts as our second cache, L2. The L2 instance will similarly produce an intermediate trace and send logs of the cache operations to MySQL. So this process will continue until we reach the last level of cache, LL. At this point, the high-level script terminates and the experiment's complete. We then have a second script which can be run separately at any time, and that's responsible for handling metrics calculation using the logs stored in MySQL. So we take a set of device specifications, including prices, capacities, and average latencies, and calculate metrics such as average throughput using the operation counts of each experiment. The script generates all possible combinations of devices, calculates metrics for them, and then stores the final results into Elasticsearch. I'll now present some interesting and counterintuitive results obtained using our simulator. We experimented using the Microsoft Research block traces. These traces were collected at Microsoft from 13 enterprise data center servers, each containing 1 to 5 storage volumes for a total of 36 traces. We evaluated configurations using 3 types of devices: DRAM, SSD, and HDD. We used 3 models for each type of device, which we categorize as high-end, mid-range, or low-end, based on their relative performance characteristics and prices. In our evaluation plots, we labeled these using a letter and number, such that high-end DRAM would be D1, mid-range SSD is S2. The MSR traces access less than a gigabyte of data, so we use reverse miniature simulations to model workloads that are 1,000 times larger, which are much more suitable for multi-tier caching. So in this plot, we evaluate the performance of DRAM on MSR's HM1 workload. Each series in the legend contains the device labels of the configuration and its write policy in parentheses. So the WT stands for write through. So the cyan series labeled D2S2H3 represents a configuration with mid-range DRAM as L1, mid-range SSD as L2, and low-end HDD as persistent storage using write-through policy. On the y-axis, we have average throughput in kilobytes per second, higher is better. On the x-axis, we have the total scale purchase cost in thousands of dollars, lower is better. Each point represents a simulation of certain capacities in each device. So the cyan point at around $230 purchase cost and 225 kilobytes per second average throughput represents a simulation with around 32 gigabytes of D2, 62 gigabytes of S2, and enough capacity in the backend H3 to store the entire dataset of 352 gigabytes. The backend storage is the same size in every simulation regardless of the device because we need to persistently store all our data. So surprisingly, if we compare the blue and red series, we see that purchasing more of low-end DRAM for the same cost as the more expensive high-end DRAM yields overall better performance. For example, in the highlighted points, if we purchase 116 gigabytes of D3 instead of 46 gigabytes of D1, we gain around 65 kilobytes per second additional throughput. Therefore, we can see that sacrificing device performance for more capacity can sometimes produce better results. In the next evaluation, I'll show the impact of SSD degradation in multi-tier systems. It's well known that memory cells and SSD can only be written to a finite number of times before they're no longer usable. Studies have also shown that SSD aging can increase average latency by around 2 to 3 times. So to model this effect, we multiplied the latency of device S2 by 2 and 3 times and analyzed the results alongside simulations using its original specifications. The configurations used in the aged device are labeled in the legend as 2x and 3x. WT represents write-through policy, while WB represents write-back. The axes are the same as in the previous slide. So when we insert a brand new S2 in between D1 and H2, there are many configurations with improved performance for the same cost, which are the green triangles above the red line. However, when the SSD is aged, there aren't any configurations which improve performance since all the blue and cyan points are below the red line. For write-heavy workloads or infrastructures where SSDs receive a lot of traffic over a short period, choosing to exclude SSDs may not only save money, but also yield similar or better average throughput over time. I'll now conclude and mention some of our future work. In this work, we propose best practices in cache research, including the analysis of multi-tier systems and evaluation of a more comprehensive set of metrics. We extended PyMimircache into a multi-tier I/O simulator and ran simulations on 36 traces with many different configurations. We presented interesting and counterintuitive results from these simulations, demonstrating the need for multi-tier analysis and simulation. We're currently in the process of developing an N-level I/O cache simulator, as well as visual analytics tools to explore the vast configuration space of multi-tier caching. That's the end of my presentation, and thank you for listening.